All right, sorry about the delay. Good morning, everybody, and welcome back to Abstract Algebra. Today, we're going to jump into Chapter 7 and talk about cosets. As a reminder, at my usual office hours for the next 3 days, today and Wednesday, hour 4 class from 2 to 3. Tomorrow from 10 to 11:30 in the morning, 1:30 to 2:30 in the afternoon. I will not be holding office hours Thursday and Friday because it's fall break. Yes, oh snap. And it's also as a reminder, don't forget exam 1 is due Wednesday if you haven't started it yet. Oh boy. I want to get on that.
Oh my god, fresh, crisp chalk.
No, it's fresh box of chalk. How sweet.
Great.
Anybody have any questions or comments before I do the joke of the day and get started? Okay, this one's a long one. An engineer, a physicist, and a mathematician are all subjects in a psychology experiment. After not eating for 24 hours, each of them is locked in a room with a can of food, so pencil and paper, but no way to open the can. They're not given any can openers or anything. So at the end of the experiment, a long time later, the psychologist first enters the engineer's room and finds that the pencil and paper were unused, but there are dents all over the wall. Engineer just threw the can into the wall until it split open, and engineer's enjoying a nice can of beans or something. So the psychologist goes into the physicist's room next. And in the physicist's room, the paper is covered with formulas. There's only a single dent in the wall, and the physicist is also eating. Turns out that she calculated how to best throw the can against the wall, and she got it open on her first throw. And finally, they go into the mathematician's room, where the paper is full of formulas, the wall has no dents in it, the can is still closed, the mathematician is nowhere to be found, and there's strange noises coming from inside the can. The psychologist quickly opens up the can, the mathematician jumps out and immediately says, "Ah, thank you for saving me. I guess I got a minus sign wrong somewhere." Let that be a lesson. Let that be a warning to you all about misplacing your minus signs. Okay, so before we get started with the new stuff, I thought we'd finish the theorem I started proving last time but didn't quite finish up, which was the theorem in the last packet which said if phi from G1 to G2 is an isomorphism, and G is an element in the first group, and then the order of G is equal to the order of phi of G. So we started proving this at the end of class on Friday. In fact, I showed it in the case where G has infinite order. Proved that if G has infinite order, then phi of G has to have infinite order. But I just want to finish off this proof by doing this second case, which is what if G does have finite order n? So in our proof, this is just going to be the second case, which is the order of little g is equal to some finite number n. Meaning, if you take g star g star g enough times, you will eventually get the identity element. Well, so if the order of g is equal to n, I claim for any positive integer k, if g to the k is the identity in the first group, I claim that that's going to imply, and in fact be a two-way implication, that phi of g to the k is equal to the identity element in the second group. The reason here is that if g to the k is the identity, well, phi of the identity, we know that as a homomorphism, phi has to map the identity of the first group to the identity of the second group. And so if g to the k is the identity in the first group, phi of that is going to have to give you the identity element in the second group. And similarly, the same argument is an if and only if, because phi is 1-to-1, meaning we know E1 has to map to E2 under our isomorphism. But since it's 1-to-1, nothing else can map to E2. And so if phi of g to the k is the E2, g to the k would have to be equal to the identity in the first group. I know I'm not writing all that down, but I kind of want to get through this quickly so we can get to the new exciting stuff for today. Any questions about why g to the k is the identity in the first group is equivalent to saying phi of that same thing is the identity in the second group? Well, since we can use a lemma from last time, the lemma that said phi of g to the k has to be equal to phi of g to the k. And so that's going to be equivalent to saying phi of g raised to the k power is the identity element in the second group. And so what we end up with is that g to the k is the identity in our first group if and only if phi of g raised to that same power gives us the identity element in the second group. And from that, this basically follows very quickly, because we can then just say, thus, since n is the smallest power, is the smallest, let's say k greater than 0, such that g to the k is the identity element in the first group, and must also be the smallest k greater than 0, such that phi of g raised to that power is the identity in the second group. Basically saying, whenever g to the k is E1, phi of g raised to that same power has to be E2. So if we know that n is the smallest power for which that happens, for which g to the k is the identity, it has to also be the smallest power for which phi of g raised to that power is the identity in the second group. It's because relying heavily on this equivalence here. Basically saying whatever's the smallest one that'll get you to the identity in one group has to be the same as the smallest number that'll get you to the times that'll get you to the identity in the second group. And so thus, the order of phi of g has to also be n, which is the order of g. What? All right, I should have known better for looking in Elaine's general direction.
I'm just smiling.
Good. Any questions or comments here? So basically, what this theorem then tells us, wow, I did not give you any time to answer the question of any questions or comments. Basically, what this theorem tells us is that if you have an element in the first group of order like 5, then whatever the isomorphism maps that to in the second group, it also has to map to something of order 5. And one of the many ways in which whenever you have an isomorphism between two groups, it tells you a lot about the relationship between the two groups. It's all part of the, and if two groups are isomorphic, then mathematically they're the same and have all the same properties that we care about. All right, it's going to do it for isomorphisms for now. We are going to come back to isomorphisms later when we get to one of the big theorems of the semester, GAD, or as you might, or as it is written out, the fundamental theorem of finitely generated abelian groups. But today I want to talk about cosets. So there is a new packet. Hopefully you picked one up over by the door. What we're going to do in this packet is we're going to prove Lagrange's theorem, which is kind of the big theorem that says the order of any subgroup has to divide the order of the group. You may remember we proved that for cyclic groups as part of the fundamental theorem of cyclic groups, that if H is a subgroup of G, then the order of H has to divide the order of G if G is a cyclic group. Turns out that that theorem is going to be true in more generality. And we're going to use this new idea of what's called cosets in order to be able to prove that that holds true in any group, or any finite group, I should say, that the order of a subgroup has to divide the order of the group. Let's do some cosets. So for cosets, we're going to start out by letting G be a group. And H is going to be a subgroup of G. And we're going to say that a left coset of H in G is a set of the form little a times H, which is a set of all elements of the form little a times little h's, where little h is an element in big H, for some fixed element a in the group. And similarly, we can define right cosets of H in G. Blah, 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 blah. It's going to be a set of all elements in H multiplied on the right by some fixed element A. One will give you an ah, and the other will give you a ha. So when you combine them, you get a good laugh. Yes, just like that. So let's look at an example. These things are going to have some interesting properties to them. So, as an example, I'm going to look at the group G is just going to be the dihedral group on triangles. So E, R squared, S, RS, and R squared S. H, our subgroup, is just going to be the group consisting of the identity element and R times S. And what I would like to do is to calculate what elements lie at a few different left and right cosets of this subgroup. So this is going to be a left coset. You can tell if something's going to be a left coset if you have an element in your group multiplied on the left-hand side of the subgroup. This will be a left coset of H. So in general, if you want to find what elements lie in a coset, you just have to take all your elements in your subgroup, H, and just multiply them on the left by whatever elements out in front here. So in this case, all. So since our two elements in H are of the form identity element and RS, we just need to take both those two elements and multiply on the left by the group element R. And that will give us a coset. So if we took R, 120-degree rotation in the dihedral group D3, and we multiplied by the identity element, what are we going to get? What do we always get when we multiply by the identity element? R. Yeah. Anything times the identity element is whatever the other thing is. How about if we take R and compose it with RS? Yes, Megan?
R squared S?
Yeah, just R squared S. And so this left coset is just going to be made up of the set containing the elements R and R squared S. Whatever we got when we multiply E and RS on the left by a single element R. Let's take a look at a right coset. So that gave us the r. This will give us the her. So when you're looking at right cosets, it's the same idea. You take everything in your subgroup, in this case, everything in H. Except this time, instead of multiplying on the left-hand side of those elements by, say, R, we're going to multiply everything on the right-hand side by r. So, someone other than Megan. We know that if we took R and compose it with E, we get the symmetry R. What if we compose E with R? Okay.
We still get R.
We indeed still get R. Not this one though. RSR. RS times R. That's not one of our 6 elements, that, or at least in the way it's written. Well, here we have to do what we do with the dihedral group and be clever. In which we can use that RS times R is the same as R times SR by using some associativity. We can then use the fact that SR is equal to R squared S in D3, as we've seen, and then write that out as being R times R squared S, which will give us, what, R cubed times S. And if we take R cubed, compose it with S, what does that simplify to in D3? Okay. Yeah, because R cubed is just the identity element. If you rotate 120 degrees 3 times, you get back, that's the same as doing nothing. And so we end up getting back just an S for RS times R. So that'll give us a right coset. Your job is to take a few minutes and find what elements lie in these other 6 cosets on the front page. SH, his, RS times H times RS, R squared H times, and HR squared. And then, after you do that, I want you to take a minute and reflect upon, what do you notice? Do you have any observations between the difference between left and right cosets, between all the different left cosets, between all the different right cosets? I want you to see if you notice any patterns. Go take a couple minutes and work on that. And if you're feeling like stuck or confused on something, as always, feel free to flag me down.
Hello, Lauren.
Elaine will kick you out of this class. Hello, everybody who is watching this remotely. Encourage you to try these out for yourself, get you some good practice, and see what observations you can make, and see if you agree with the observations we're going to make here as a class here in a few minutes. Give it a try. And don't be afraid to use the fact that SR is equal to R squared times S. That might be useful at a couple different points. Once you think you have all the cosets, see if you notice anything that strikes your eye in looking at the left versus the right cosets, or the left cosets in comparison with each other, say.
Yeah. So I was thinking, what does that turn into? You could do multiplying by like these and multiplying by the other. Okay.
I just took out,
Cool.
I just took RS.
Okay.
Because like the only thing that I'm seeing
Okay,
is like
interesting.
like the same thing. Right, and I think that's because it's the only.
Give me the other one.
That might just have to do with the dihedral group. I don't know if that's to do with. I don't know that it'd be the same thing. Otherwise.
Which one are you doing? R squared S, RS, SR.
Oh, maybe
RS.
they're gonna be the same if it's
Okay.
abelian element. I want to start feeling to be joined. That's what we just say. Left and right.
We got a bunch of R squared S's.
I mean, yeah. I'm wondering if this has to do with abelian. I might be
Oh, we can get rid of first.
Ooh, what's this? I hear about a billion?
chameleon.
Oh, right, yeah.
Oh, chameleon.
R squared S.
So you're looking at chameleon
R
groups. Interesting.
Yeah.
Groups that may look like one thing, but surprise, they're actually the other. Sort of like the isomorphism example on the front page.
Okay.
Or maybe they're lizards. Yes.
Oh, S, R squared, and R squared S. Those are like the opposite of each other.
Okay, so if the whole group is abelian, then the RS is the same.
And you got RS and
Right.
SR,
No matter
which
what
are the opposite of each other.
So if the left
Here's the
right
patterns.
cosets have the same, if the same H value for the right, H,
Yeah,
same
these are
J
patterns
value for
that
the left
these
right coset.
Right.
No.
That's not
The
right.
same output, then it's
Awesome.
okay.
Oh, you're done.
No, that's right, yeah.
Yes.
You put an
Oh,
S
what
here,
are you
R
looking
squared,
for?
you put an
I
R
don't know.
squared,
Can
yes.
do any of these equal each other?
Oh, so like when you're using that first. Yeah.
Across
Right.
or up and down? Any of the left cosets equal any of the other left cosets? Do we need the left cosets equal the corresponding right cosets? All things to why is it so quiet in here considered?
Would you like me to fix that?
No.
That's what I thought.
Go ahead and take about another minute or so, and then we'll come back together as a class.
Yeah. are closed. Let's do some of this with like game versus.
Yeah, so the thing is like. Somehow maybe. I don't know. Well, not inverse physics. What would be inverse physics? Corresponding inverses? Like, we are squared as, this would be a piece of that.
Okay, let's come back together and talk about these as a class. So, if we were to take the left coset of H where we multiply by S, we would get S times the identity and S times RS. What elements would that simplify to? If we were to take S times E and S times RS. Right?
S R squared.
S and R squared?
S and R squared.
Indeed. What about if we took our the same coset, but on the right this time? We take everything in H and multiply it on the right by S. What would we end up with? Peter?
S and R.
It is going to be S and R. Okay. What about if we multiply H on the left by R times S? What is that going to simplify down to?
That R S and E.
It's going to simplify down to RS and E. What about if we take H and multiply it on the right by R times S? Okay.
It's the same thing. E and RS.
Hey, it is the same thing. How about that? R squared times H?
R squared and S.
R squared and S? Huh. How about if we take H and multiply it on the right by R squared? Thank you.
R squared and R squared S.
Okay, cool. Okay. Anybody have any observations? Nice job. Anybody have any observations that they made kind of looking at the relationship between these left and right cosets? Heard some good comments as I was walking around the room, so I know you're just playing possum. You also may have noticed that I threw some provocative equal signs and not equal to signs. So let me start this up. What can we say about the relationship between AH and HA? Are they always going to be equal? Are they never going to be equal? Are they sometimes going to be equal? If we were to take H and multiply the left and right by the same element. Wayne?
They're going to be equal only if A and all the elements of H are abelian.
Are abelian to each other. You mean commute?
Yep.
No.
Oh.
They happen to work out that way in this example, but in the one example I gave you. But it turned out to be the case that the elements don't necessarily have to commute, which we will see later. So it turns out the left and right coset for AH and HA, they're sometimes equal, but not always. I think that is a good observation. I'm glad you made it. It's worked out in this example, but it's not going to work out in every example. But the elements have to commute individually. Sometimes the elements don't commute, but you still get the same coset. Maybe in the opposite order. What else do I want you to notice? What if we have two different elements, A and B? Is it possible that they generate the same left coset? / is it required that they generate the same left coset? / do they never generate the same left coset? According to what we've seen. Kelly?
Sometimes, but not always.
Yeah, I would say it's possible that they're equal to each other, even if A and B are different elements. For instance, it turned out that R squared H and SH generated the same left coset. In both cases, we ended up with a set containing the elements R squared and S. So Dr. Gerstel, here it's R squared and S, here it's S and R squared. It's the same coset. The order of the elements within the set doesn't matter. It's the same collection of elements. The fact that here we got S from the first product and R squared from the second product, versus here we got R squared from the first product and S from the second product, ended up, the order in which we got them doesn't matter. It's the same elements in the end. So in this case, we would say R squared H and SH are the same coset of H. It's generated in different ways. But if we were to compare that to RH, these are not the same coset because this is not the same set of elements as SH. Do left and right cosets have to form subgroups? So we found lots of, 4 left cosets, 4 right cosets. Do we know if those are all of these cosets that we found subgroups? / are any of those cosets that we found subgroups? Wayne?
Not always, because with the second two don't have the identity element in them.
Yeah. These last two, as well as the first 4 cosets, none of those have an identity element in them. So none of those are going to be subgroups. Whereas this one, the left and right cosets of H, where we multiplied left and right by RS, those did form subgroups. In fact, they gave us back the exact same subgroup we started with, H. So, so it's going to turn out to be the case that AH and HA may be subgroups of G, but don't have to be. And what was my last observation? Oh yeah, what can you say about the size of all these cosets? How many elements are in each coset? Yeah.
As many as the original subgroup.
Yeah, all of the cosets of H are, and this is going to be a property that holds true in general, all the cosets have the same size, the same order as the original subgroup. So these are kind of some interesting properties about cosets that I kind of wanted you to hopefully get a sense of from just playing around with them a little bit. That that if you take the same coset but on the left versus on the right, they may be equal but don't necessarily have to be. Two left cosets may be equal to each other even if they're generated by different elements. They could be, but they don't have to be. Cosets in general are not going to be subgroups of G. Spoiler alert, they're subgroups of G if and only if they're equal to the original subgroup, H. And finally, all cosets are always going to have the same size. And so if you flip the page to second page of the packet, here's a heaping list of properties that cosets are actually going to have that kind of get at a lot of these observations you all made. So if H is a subgroup of G, little a and little b are elements of G, then any element is always going to be an A coset. So little a is always going to be contained in the coset, the left coset AH, and also the right coset HA. Two cosets AH and H are going to be equal to each other if and only if A is an element in H. So if you try and take a left coset by an element or a right coset using an element of the subgroup, then you're just going to get back the same subgroup. Just like what happened in this case when we took little rs times h versus h times little rs. Since little rs was already an element in the subgroup h, when we multiplied h on the left by it, we just got back h again. That's going to be a general property. Property 3 basically gives us some associativity conditions to looking at cosets. Property 4 gives us a condition under which two cosets will be equal. Little ah equals little bh if and only if A is an element of bh, and vice versa. Number 5 is the fun one. I'm going to come back to that one. Number 6, two cosets are equal if and only if A inverse B is an element in H. So number 7 says all cosets have the same size. Number 8 says equals ha if H equals aha, inverse. And 9 basically is kind of getting at the thing I hinted at the end, where H is a subgroup of G if and only if A is an element in H, which is true if and only if AH equals H. So the only time where you can take a left coset of H and get another subgroup is if the left coset just happens to be the same subgroup you started with. And then there's number 5. Ooh, number 5 is my favorite. We're going to prove number 5. Which is if H is a subgroup of G, A and B elements in G, then AH is equal to BH if and only if AH and BH have non-trivial intersection. Dr. Gerstle, that's a lot of squiggly nonsense at the end. So what this means when we say AH intersect BH, remember this is the set of all elements that are in both of the two sets, both the two cosets, AH and BH. When we're saying AH intersect BH is not equal to, this is a symbol for the empty set, the set with no elements in it. Basically what we're saying is these two sets have at least one element in common. And so what this theorem is saying is that if two cosets have at least one element in common, then they have to be the exact same coset. Two cosets have at least one element in common, then they must be the exact same coset. So it's not possible to have two cosets that say, let's say the two cosets have just a single element in common. Now, it's all or nothing when it comes to cosets. Either they are disjoint, they have no elements in common with each other, or they have all elements in common with each other because they're the exact same set of elements. So if we were to do a quick example, let's say our group is S3, and our H this time is going to be made up of A3, instead of all even permutations in S3. So this is just an example if you want to write over to the side. We're going to do an example, and then I'll prove this theorem. So H is the set of all even permutations in S3. Remember, even permutations means it can be written as a product of an even number of two cycles. So here, this is just going to be 1, 3, 1, 2. This is just going to be 1, 2, 1, 3. All of these can be written as a product of two cycles. Identity, pick any two cycle, multiply it by itself. You'll get the identity. Let's take a look at our cosets of H and G. If we were to take 1, 2, 3 and multiply by H, without doing the multiplication, and instead by using number 2 from the lemma, what can we say that this has to be equal to? If we were to take the subgroup H and take the left coset of H, where we multiply everything on H on the left by the 3 cycle 1, 2, 3. Right? It's just going to be H, because since 1, 2, 3 is already an element of H, when we multiply H on the left by that element, we're going to get back H. Which, for the same reasoning, by the way, we're also going to get the same as 1, 3, 2 times H, and the same as the identity element times H. In all cases, we're going to get the same set of elements. Identity, 1, 2, 3, and 1, 3, 2. If we were to multiply H on the left by either 1, 2, 3, 1, 3, 2, or the identity. On the flip side, if we were to take, say, 1, 2 times H, well, I actually claim if you multiply H on the left by any 2 cycle, you're going to get the same set of elements. It's going to be just all the individual 2 cycles. So, turns out H is only going to have 2 distinct cosets. The coset that's just equal to H itself, and the coset that's not equal to H, the one where you just get 1, 2, 1, well, the individual 2 cycles. And if you notice, you compare any of these cosets with each other. These 2 cosets, for instance, are the exact same. But if you compare 1, 2, 3H with, say, just 1, 2H, these 2 cosets have nothing in common. Kind of leading to what this property 5 says. If you're comparing 2 cosets, they either have to be the exact same, or they have to have no elements in common with each other at all. In this case, you compare any 2 of these, you're going to get the exact same thing. Just like if you compare any 2 of these 3, you're going to get the exact same set of elements. But if you compare anything from one of these top cosets with anything from with any of these bottom cosets, they have no elements in common. This does not contain anything from up here and vice versa. So that's kind of an interesting property of cosets that's going to be useful to us. Let's stop for a second. Let's see what questions you all have.
Is it true for all these properties that the left, they're all given as the left ones that are given as the left coset version, or is this true for right coset?
Yeah. basically all the same arguments work for right cosets. You might have to change up the ordering a little bit for some of these. But you could say like big HA equals big HB if and only if A is in big HB would be a true statement. As algebraists tend to work with left cosets unless they're weirdos. So I like to write things in terms of left cosets, but you could rewrite a lot of these properties, and the same properties would be true of right cosets because they're not inherently different from each other. Heard someone say something about abelian groups as I was walking around the room here earlier. If you're working in an abelian group, then all the left cosets are exactly the same as the right cosets. But that's kind of boring because they're just the same thing. Cosets are a lot more fun and exciting when left cosets and right cosets are different from each other. It is possible to have a subgroup, a non-abelian group, and a non-abelian subgroup where all the left and right cosets are equal to each other. That's going to give us an example of something that's called a normal subgroup. For instance, this would be an example where all the left cosets of H would be the same as all the right cosets of H, even though H and G are not abelian groups. The left and right cosets still come out to the same. That's going to be a very important type of subgroup to us. And here's why. Normal subgroups are nice because those are going to be subgroups that we can divide by. A few weeks from now, we're going to be talking about how you can multiply two groups together to get a new group. We're also going to talk about how you can take a group and divide by one of its subgroups to make a new group. I'm going to leave you all with that thought. Have a good day, everybody. When we come back on Wednesday, we're going to prove this theorem number 5 that I didn't quite get to. And we will also prove Lagrange's theorem, the big theorem that tells us the order of any subgroup has to divide the order of the group using this lemma about cosets. Y'all have a good day. I'll see y'all on Wednesday.